When engineers describe desalination as low carbon, the first question should not be which membrane is being used. The first question should be what system are we measuring, and what conditions does that measurement represent? Desalination is part of a wider water security system. It can contribute to water availability, but it is not an isolated answer. Its energy demand, electricity source, pretreatment, recovery, pumping, and discharge pathway all influence the overall result. The environmental question is therefore not limited to the product water line. It includes the concentrated stream leaving the process and the conditions under which that stream enters the receiving environment. This episode focuses on seawater reverse osmosis, energy recovery, and brine management. The objective is not to present a universal plant design. It is to develop a disciplined way of thinking about performance. We will distinguish a reported energy range from a guaranteed value. We will separate the physical principle of reverse osmosis from the engineering decisions around it. And we will distinguish technologies that are commercially applied from resource recovery concepts that remain promising but dependent on readiness, economics, corrosion, and product quality. A useful starting point is humility about comparisons. A number expressed in kilowatt-hours per cubic meter may include some process steps and exclude others. A carbon intensity claim may change when the electricity source changes. A higher recovery rate may reduce the volume of brine while increasing salinity, scaling, and operating risk. In other words, low-carbon desalination is a system property, not a label attached to one component. Reverse osmosis is best understood as a pressure-driven separation process. In ordinary osmosis, water moves across a semi-permeable membrane in response to a difference in chemical potential. In reverse osmosis, applied pressure drives water in the opposite direction, producing a permeate stream while retaining a more concentrated stream. That description is physically useful, but it is not yet a plant description. A real desalination system includes more than the membrane surface. It includes the condition of the feed water, the steps used to protect the membrane, the equipment that supplies pressure, the treatment of the product stream, and the management of the concentrate. The membrane is therefore one element in a chain of dependent functions. The engineering distinction matters because a membrane can be described as efficient while the complete system carries additional energy and environmental burdens. The boundary of the calculation must be stated. Does it include only the basic reverse osmosis steps? Does it include pretreatment, pumping, post-treatment, and discharge? The answer changes the meaning of the reported result. The International Energy Agency describes a transition toward reverse osmosis and electrical systems in desalination. That transition is significant because it makes electricity a central part of the performance discussion. It also means that the water sector must avoid treating electrification as an automatic synonym for decarbonization. Electricity has an emissions profile, and that profile depends on its source and on the boundary used for the assessment. For technicians and engineers, the practical lesson is to draw the process boundary before interpreting a performance number. Mark the feed, the pretreatment, the pressure-producing equipment, the membrane separation, the product water path, the concentrate path, and the energy recovery function. Then ask which of those elements are included in the comparison. Without that discipline, two apparently precise figures may describe different systems. Energy is often the first metric used to discuss low-carbon desalination. The International Energy Agency reports an approximate range of 2.5 to 6 kilowatt-hours per cubic meter for seawater reverse osmosis, including basic steps. This range is useful as context, but it must not be presented as a universal plant value or as a performance guarantee. The range exists because desalination systems do not operate under one set of conditions. Design choices matter. Feed water conditions matter. Pretreatment matters. Recovery matters. Pumping matters. The definition of basic steps matters. So does the volume used in the denominator. The comparison may be expressed per cubic meter of product water, but the energy is consumed by a system that also handles feed water and produces concentrate. A professional narration should state the technology, the included steps, the operating context, and the boundary of the calculation. It should also distinguish measured performance from an approximate literature range.
In a pressure-driven process, the concentrate stream leaves the membrane system with energy associated with its pressure. Energy recovery is the engineering function that seeks to use part of that available hydraulic energy rather than treating it as entirely lost. The principle is straightforward. Reduce the external energy required to provide pressure by transferring or recovering energy from the pressurized concentrate pathway. The principle, however, should not be turned into an unsupported promise. The value of energy recovery belongs inside the complete system calculation. Its contribution depends on the process arrangement, the pressure pathway, the equipment interfaces, and the defined boundary. A narration that says energy recovery makes desalination low carbon is too broad. A more accurate statement is that energy recovery can be an important part of reducing the energy demand of a pressure-driven system, while the final result remains dependent on design and conditions. The same discipline used for specific energy applies here. Identify the energy entering the system. Identify the pressure-producing function. Identify the concentrate path. Identify where recovered energy is transferred and which losses or auxiliary demands are included. Then compare like with like. The purpose of this explanation is conceptual, not operational. The appropriate equipment selection, integration, protection, control philosophy, and verification belong to a site-specific engineering process. They must account for feedwater characteristics, membrane behavior, scaling and corrosion concerns, maintenance, and the requirements of the full facility. Energy recovery also illustrates a broader lesson in water infrastructure. Efficiency is rarely created by one isolated device. It is created by coordinating a chain. Pretreatment protects the separation process, pressure equipment supplies the driving force, recovery reduces avoidable energy demand, monitoring verifies behavior, and the concentrate path determines part of the environmental consequence. Reverse osmosis does not begin when water reaches the membrane. It begins with the condition of the feedwater and the decisions made to manage that condition. Pretreatment is part of the system because membrane performance and reliability depend on what reaches the separation stage. The research identifies feedwater quality and pretreatment as factors that affect the desalination carbon footprint. That observation has an important consequence. Pretreatment cannot be treated as an invisible auxiliary. It consumes resources, introduces its own equipment and chemical considerations, and influences the stability of the downstream process. Recovery creates another central trade-off. Increasing recovery means obtaining more product water from a given feed stream and reducing the volume of concentrate relative to the feed. But the concentrate becomes more saline, and higher recovery can increase salinity, scaling, and operating risks. This is not an argument for one universal recovery target. It is an argument against evaluating recovery only through volume. A technically mature discussion keeps several questions together. What is the feedwater quality? How does it vary? What pretreatment is required to protect the process? What recovery level is being considered? How does concentration affect scaling and corrosion concerns? How does the resulting brine affect the discharge assessment? And how do these conditions change the energy calculation? These are connected questions because a choice made at one point in the system changes the burden elsewhere. A higher recovery may reduce the quantity of brine, yet it may make the remaining stream more concentrated. A change in pretreatment may influence membrane protection and auxiliary demand. A change in pumping or discharge arrangement may alter both energy use and environmental evaluation. Brine is a design responsibility, not a final stage afterthought. Highly saline concentrate and associated chemicals may harm coastal ecosystems without appropriate assessment, mitigation, and monitoring. The relevant engineering discussion includes the receiving environment, site selection, dilution, diffuser concept, monitoring, permits, and uncertainty. These elements are coordinated, not interchangeable slogans. Resource recovery from brine may be promising in some applications, but promising does not mean universally commercial, economically proven, or ready for every site. Readiness, economics, corrosion, product quality, and the remaining residual stream all require evaluation. Let us close with an engineering framework. Define the service, product water, and its role in the wider water security system. Define the system boundary before quoting energy. The approximate energy range for seawater reverse osmosis provides context for basic steps, not a universal guarantee. Describe the process as a chain. Feedwater quality influences pretreatment. Pretreatment influences the membrane system. Pressure production influences energy demand. Energy recovery can reduce avoidable demand within the pressure pathway. Recovery changes product water yield and concentrate characteristics. Pumping and discharge connect the process to the receiving environment. Separate energy from carbon. Energy is measured in kilowatt hours. Carbon implications depend on the electricity source and on what the life cycle assessment includes. Treat brine as part of the design responsibility. Be precise about uncertainty. Higher recovery can reduce concentrate volume while increasing salinity, scaling, and operating risks. A technology can be mature in one context and unsuitable in another. The final lesson is that low-carbon desalination is not achieved by choosing a membrane and adding a slogan. It is pursued by making the system legible, clear boundaries, transparent energy accounting, careful consideration of electricity, integrated recovery and pretreatment decisions, and responsible management of the concentrated stream. This episode is an educational overview for professional audiences. It is not a plant design, operating instruction, environmental permit, or site-specific recommendation. Any real project requires qualified engineering review, water characterization, environmental assessment, applicable authorization, and verification against project conditions.
An engineering review becomes more useful when it converts a broad sustainability claim into a sequence of specific questions. What is the water service being delivered? What feed water is being considered? Which pretreatment functions are within the system boundary? Which pressure-producing and energy recovery functions are included? What product water quality objective is relevant? What concentrate remains, and what receiving environment must be assessed? These questions create traceability. They allow two configurations to be compared without pretending that one headline metric resolves every trade-off. They also clarify where additional evidence is needed. A change in feed water quality may change pretreatment demand. A change in recovery can change concentrate characteristics. A change in electricity supply can change carbon implications without changing the membrane itself. A change in discharge conditions can alter the environmental assessment even when the product water line looks the same. The value of a systems perspective is not that it makes desalination seem simple. Its value is that it prevents a simplified claim from hiding a meaningful dependency. Engineers and technicians work with dependencies every day: water quality, pressure, materials, monitoring, maintenance, environmental authorization, and the ability to verify real behavior over time. Those dependencies should be visible in communication as well as in design documentation. In practical project work, a disciplined evidence record can connect the process diagram, water characterization, energy accounting, environmental assessment, and operating assumptions. It should state what is known, how it was measured, which conditions shape the result, and where uncertainty remains. This record improves handover between technical disciplines and reduces the risk that a contextual study result becomes a generic promise. A responsible discussion of innovation also uses staged language. A concept may be technically interesting. It may deserve piloting or further feasibility work, but readiness for one location, water source, electrical context, or product market does not make it ready for every location. Resource recovery from brine is one example. It may offer a future pathway, but an engineering decision still needs to consider product quality, materials compatibility, corrosion, energy, economics, residual management, and environmental context. The most durable conclusion is therefore not that one desalination configuration is always best. It is that good engineering makes the boundary visible, measures energy honestly, evaluates trade-offs, and treats the concentrated stream as a responsibility rather than an afterthought. That is how a water security decision can remain technically credible while acknowledging its environmental and operational conditions.
The purpose of this episode is not to reduce desalination to a slogan. It is to support clearer questions, more transparent comparisons, and responsible engineering judgment. Water Atlas connects technical evidence with the wider infrastructure decisions that depend on it. Evidence, boundaries, and responsible review remain the foundation of every credible water infrastructure decision. Water Atlas, Engineering knowledge for informed water decisions. Evidence-led engineering makes water decisions more resilient.